So we are going to start. The second session of Tuesday. It's about hardware implementations. This is one of the most wonderful areas in implementations of elliptic curve and pairings. And we have two talks for this session. We will start first with Dr. Jérémie Detrey from INRI and NC, and he will talk us about implementations of pairings over supersingular curves. So please, Jérémie.
Thanks. Is it okay like this? Not too loud. Okay, so first of all, thank you, Francisco, for the introduction. I would also like to thank the scientific committee of ECC for inviting me here. It's really a pleasure to be standing here in front of you. Thank you all for coming as well. So the work I will the work I will present this morning is actually a compilation of several works done in collaboration with many people, but I think the 5 most important ones are here. So there is Diego Aranha, who is now at the University of Brasilia, Jean-Luc Bechat from University of Tsukuba, Nicolas Brisbard and Nicolas Thibal, who are now in Lyon in France, and of course Francisco Rodríguez-Henríquez, who all of you know by now. Okay, so a bit of context and motivation for this work. So maybe you all, I guess, you are all already familiar as to how pairings came into cryptology. So first of all, they were introduced at an attack against supersingular curves, and since 2000 they are now used in many, as cryptographic primitives in many protocols. Well, of course, these pairings are used in different applications, and those different applications require different kinds of devices. So, for instance, if you're working in embedded systems or smart cards, like say your credit card in your pocket, if you wanted to implement pairing on them, well, you'd have a very low resource environment, so you'd have to be very careful about the resource usage which you will need to implement your pairing. And on the other hand, you can imagine several scenarios, such as in bank servers, where they might have to verify many signatures in a second. You might imagine very high performance computations. So pairings are still a very expensive computation, first of all because of their complex mathematical structure, also because they require both finite field and elliptic curve arithmetic. And well, for finite field arithmetic, well, the basic operations that you might need are not available on your everyday processor, and I'm not even talking about what you have available on a smart card. Which means that there is a strong need for hardware acceleration. So by hardware acceleration, I mean the design of a dedicated coprocessor with a custom arithmetic data path. And the advantage of being able to do hardware acceleration is that since we design the circuit, we have a very large design space to choose from, and we can balance various trade-offs depending on the actual application at hand. So in this talk, I won't cover everything in I won't target all the possible applications and all the possible trade-offs that one might encounter in implementing pairings, and I will focus actually on 2 points. First of all, reaching the 128-bit level of security, and also designing a compact accelerator. So the outline of my talk will do the following. I will start with some definitions, but actually most of them were already covered on Sunday by Craig and Francisco's talks, so that would be quite fast. Then I will show you first basic implementation, what we could do in a, I would say, naive way of implementing the pairing. And then I will detail 2 recent advances. The first of them, which was published by Nicolas Thibal at Pairing 2010, and the second one, which was published this year at CTRSA by Diego Aranha, Nicolas Thibal, Jean-Luc Bechat and myself. Okay, so pairings, just to set the notation straight. So, well, first of all, I will need 3 groups. G and G prime will be noted additively, and GT will be noted multiplicatively. All these groups will be cyclic and of order L. Then a pairing will be defined as a map from G and G prime to GT, satisfying the following properties. So, well, obviously you want it to be computable. You want also this pairing to be non-degenerate, otherwise it's a bit pointless. And last of all, the most important property is the bilinearity of the pairing, which is if you take the pairing of ops R prime and S, you can rewrite it as the product of a pairing of R and S and R prime plus S, and have the same kind of linearity on the right-hand side. And the immediate consequence of this bilinearity, which is actually the key property of pairings, which is used in cryptographic protocols, is that if you have the pairing of K1 times P and K2 times Q, then you can just take the K1 and K2 and put them as exponents of the pairing. Okay, so let me get a bit further on the details and define the Tate pairing. So we'll start with an elliptic curve E defined over a finite field FQ, and we'll take L to be a large prime dividing the group order over FQ. So what we can define with this L is the L torsion subgroup, which is the set of points of order L, and the L roots of unity, which are the points, the elements of the algebraic closure of FQ of order L. Then we define the embedding degree, which is the smallest case such that L divides Q to the K minus 1. And so immediately we have that, actually all the roots of unity are defined over the kth power extension of FQ, so FQ to the K here. And also if this embedding degree is larger than 1, then we also have that the whole L torsion is actually FQ to the K rational. And so we can then define the reduced Tate pairing. So there are a few extra conditions here which I won't detail. As this map, so the first group will be the FQ rational L torsion, the second group will be the FQ to the K rational L torsion. And so this ensures that we can take P and Q living in different subgroups. And the result of the Tate pairing will be in the L roots of unity, and it will be computed as this. So this FLP of Q to this power, where this FLP notation actually denotes a Miller function, and a Miller function FNP is a rational function such that its divisor is that one. And in fact, if you look at this divisor, since P is of order L, you have that the divisor of FLP is actually just LP minus L point at infinity. So the Miller functions actually, they just denote the difference between the divisor, so here P minus O when you multiply it by N, and its corresponding reduced divisor where you integrate the multiplication by N here. So this Miller function can be computing using an inductive identity, so which is written here, and basically is just being able, when you are given Fnp and Fn prime p, you're able to compute Fn plus n prime p by just multiplying by this extra function here. And this function actually comes from the addition of np and n primes p. So if you have the 2 points here, well, you know the chord and tangent law for adding 2 points on the curve, and then you have here this blue line, which is noted L here, and this green vertical line, which is barely visible, which is V. You have to trust me here. And here your extra term will be just the quotient of those two lines. And so basically, computing F and P just boils down to multiplying P n times and keeping track of all the lines, all the extra lines that you have. So if we want to compute NP, well, we can resort to a double and add algorithm, which means that we will have an algorithm in log 2 of n iterations. So here is the basic idea behind Miller's algorithm. So you're given n as and it's two-ary binary decomposition, and you're also given a point and a curve. And so, well, the basic double NAT algorithm, if you want to compute n times p, is this one. And if you want to compute, instead of n times p, the function fnp, then you just add those 3 lines here. So we start with 1, and then for every doubling, you square the function and multiply by the corresponding extra term. And every time you need to add p, you just multiply by this extra term as well. And since the pairing is actually the evaluation of fnp at a point q, you can also integrate the evaluation directly into the algorithm. Okay, so now let's review a bit the security of all the groups involved in the pairing computation. So your pairing, as I said, is defined from 2 bits of the L torsion here and goes to the else roots of unity in FQ to decay. So the first attacks that we can consider is on the curve, so on the L torsion here. And the only attack that we know of is Pollard's row, which has complexity root of pi L over 2. And since L was taken to be a large prime dividing the group order, we can assume that L is very close to Q. And so we can replace this by root by Q over 2. And so this is an exponential complexity. Here, no surprise. The problem arises when considering the attacks on the target group, so GT, which is the L roots of unity, and actually it's a subgroup of the multiplicative subgroup of the finite field FQ to decay. And so for finite fields, as you may know, we have sub-exponentials algorithms. Right. Okay. Bye-bye. So yeah, we have sub-exponential algorithms, namely NFS and FFS, which have an L1/3 complexity. So yeah, the complexity of the attack is sub-exponential in Q to decay, meaning that this embedding degree k here will act as a cursor to balance the complexity of the attacks. So if your k is too large, then basically your computations in the group at the end are too expensive and it's just for nothing. And on the other hand, if k is too small, then your curve is subject to an attack, a discrete log attack by going through the else roots of unity here. And this was the point of the Menezes, Okamoto, Van Stone, and Freyruck attacks. So for instance, if we want to target the 128-bit security level, well, you can work out those 2 complexities here, try to balance them, and find out that k equals to 12 is the best choice that you can have for reaching 128-bit security. But this is only for prime fields. Actually, if you're over a small characteristic field, well then FFS is the algorithm to solve the discrete log over the finite field, and it has a slightly lower complexity. This C here, the constant here, is slightly smaller, which means that you have to go to higher fields, so sorry, to higher embedding degrees, such as 18 or even 24. Okay, so but the point of this talk is actually to focus on supersingular curves. So what's a supersingular curve? So you have your curve here over FQ, and I denote just Q to be P to the M, P being the characteristic of the field. So a curve is said to be supersingular when its P torsion is actually trivial, meaning that E of P is just is simply the point at infinity. So a good thing about supersingular curves is that they have a very efficient multiplication by P. So instead of doing double NAD algorithms for scalar multiplication or for the Miller's algorithm, we can devise P-ary scalar multiplication and P-ary Miller's algorithm. Another important property which is specific of supersingular curves is that they enjoy distortion maps. So distortion map is an endomorphism which is easily computable from the curve to itself, and such that if you take any point P on the FQ rational air torsion, so P obviously different from the point at infinity, then this distortion psi will map this point to another point of the L torsion, but not FQ rational. What it means is that this psi map will provide you with a non-rational map from the FQ rational L torsion to the FQ to the K rational L torsion. And so the whole point of this distortion map is actually that we can use it to construct symmetric pairings, so also known as type 1 pairings, since they are actually required by some cryptographic protocols. So here is the usual definition of your pairing. So you have here the FQ rational L torsion, and here the FQ to the K rational L torsion. Well, if you want a symmetric pairing, what you want is to have exactly the same groups here and there. So what you can do is just use the distortion map, and instead of taking your point Q in the FQ to the K rational L torsion, take it in the FQ rational L torsion and map it through psi to the FQ to the K rational L torsion, like this. So you end up with P and Q starting from the same cyclic group, and just here having to apply the psi map before computing the Miller function. Okay, so these are two great advantages of supersingular curves, but then of course there's a huge drawback, is that their embedding degree is actually bounded. So if you're over a prime field, you cannot do better than k equals 2, and if you're over a binary field, the best you can do is 4, and ternary field, the best you can do is 6. So we are actually very far from the 12 or even 18, 24 that we should have if we wanted to balance the security at the 128-bit level. But on the other hand, those supersingular curves, since, so those over F2 and F3 to the M, since they have a bounded embedding degree, it means that at least, we can still use them for pairings. And actually, binary and ternary field arithmetic is something that we enjoy when we talk about hardware implementations. They are much easier to implement than large prime arithmetic. Okay, so let's give you two examples of the curves that we will follow along this talk. So the first one is a binary supersingular curve. So, well, this is the equation. You don't really care about it. It's just, what's important is just that it's defined over F2 to the M, so over a binary field. The group order is this one, and as I said, the best you can do for the embedding degree is 4, and this particular curve reaches the embedding degree of 4. It also has a distortion map, and if you remember, I said that we had an efficient multiplication by P. So here the characteristic P is 2, so we have a very efficient point doubling. So here is the equation of the point doubling. You see that it only involves here 2 squarings and 2 more here, so 6 squarings all in all. And given that squaring is actually the Frobenius automorphism in F2 to the M, there are only very easy operations. And coupled with this efficient point doubling, there is also a very efficient Miller function for, corresponding to the doubling of a point. So here is the Miller function, which corresponds to the doubling of the point of coordinates x, p, y, p. And you see that it's again very simple. So actually, this Miller function, we will only consider its numerator. I won't go into the details as to why we can ignore the denominators, but you can just trust me, we can do that under certain conditions. Okay, so you have your Miller function for doubling. So, well, the first thing that you will do is your Miller's algorithm, you will implement it as a double and add algorithm. And since the curve order is roughly 2 to the M, well, you'll have basically M iterations of the Miller's algorithm. In 2007, Barreto, Stephen Galbraith, and others presented the eta-T pairing, which says that instead of computing FLP with L, the large prime dividing the group order, you can actually compute FTP instead, where T is defined like this. It's 2 to the M minus the group order, and actually it's just of the order of f2 to the m over 2, so square root of the group order. So basically, if you do that, you only have m plus 1 over 2 iterations. So it's you get a twofold speed up over the Miller's algorithm. And we have the same thing in characteristic 3, so I will go faster through this slide. So you have this curve here, which has a similar looking group order. This time the embedding degree is 6. You also have a distortion map. The point tripling is this operation, so it's actually very simple. And likewise, the Miller function for tripling is also very simple. And so instead of doing double NAD Miller's algorithm, you will do here triple NAD. And the eta T pairing also applies here. So instead of computing FLP, you compute FTP with T defined exactly in the same way, meaning that you'll only have m plus 1 over 2 iterations here also. Okay, so now we have two curves on which we would like to implement pairings. So those two curves, meaning the binary curve and the ternary curve. So how would we go about this? So first of all, the question that we want to ask ourselves is which extension degree should we choose? So those curves actually are defined over f2 to the m, f3 to the m. So which is the m that we should choose in order to hit the 128-bit security level? So on this graph, I represent here on the x-axis the security, and here the extension degree m that we should aim for in order to reach the security. So for the binary curve, it basically goes like this, and for the ternary curve like this. So if we take basically a vertical line at 128 bits, we end up with something like f3 to the, say, roughly 500. So here we've taken f3 to the 509. And for f2, for the binary curve, it will be defined over the field f2 to the 1223. So actually these estimates should be revised, since you might know that very recently Shinohara and others have presented reviewed complexity estimates for the FFS, for the function field sieve algorithm. So actually you'll hear more about this tomorrow in Ayashi's talk. And actually if you take those more recent estimates into account, you'd have that for the 128 bits of security, you have to go over 600 trits, so over f3 to the 600 and more. And for f2, you'd have to be over an extension degree over 1500. But actually, I will stay with those curves, since they are, at the moment, they are the curves that you find in the literature. So even though it is claimed that they do not reach the 128-bit security level, I will keep with these curves. Okay, so we want to compute this eta T pairing. So this is the actual expression of the pairing. And what does it involve in terms of arithmetic? So we have arithmetic over the base field, fp to the m. So fp to the m will be represented using a polynomial basis. And so actually very, very simple. And you have an extension of fp to the m, which is fp to the km, which will be represented using tower field arithmetic. So actually, this tower field representation will allow you to do all the operations here using only operations over the underlying field fp to the m. And this is actually a table representing the cost of the eta T pairing over the binary curve or the ternary curve. So here in terms of multiplications, additions, so this pth power powering is called the Frobenius automorphism on the field, and here inversion. And you can see that the complexity is actually linear in the extension degree m, except for the inversion, as there is only one inversion. So to give you a rough idea of the actual number of operations involved here, so I've taken the two examples, so f2 to the 1223, f3 to the 509, and so here you have an estimate of the number of multiplications and so on which are required to compute those pairings. So how do we go about computing these operations? So first of all, your field, as I said, is represented using polynomial representation. So your field elements in fp to the m will be polynomials modulo an irreducible polynomial of degree m. And so they will be represented using m coefficients in fp, so using 1 or 2 bits to represent coefficients over f2 or f3. The addition is actually very simple. It's just coefficient-wise addition over fp. And squaring, cubing is the pth power Frobenius, as I said. So it's a linear operation, and each coefficient of the result is actually a linear combination of the input coefficients. So to give you an example, over f3 to 509, if your irreducible polynomial f, you take this polynomial here, this trinomial here, you'll find that your, cubing a will require you to compute, for instance, this sum of 3 elements for the 351st coefficient of the result, and this linear combination for the 42nd, and so on. Another operation that is required by the pairing is an inversion, but actually there's only one inversion required throughout the whole algorithm. So instead of dedicating hardware for an actual extended Euclidean algorithm, you can just use Fermat's little theorem, and using Ito and Tsuji's algorithm, you can show that inverting only requires a few multiplications and m Frobeniuses, so m applications of this pth power Frobenius. So you can do that with already available operations. So you already have a Frobenius operator and a multiplier, so actually you don't need any extra kind of hardware to implement the inversion. So now let's talk a bit more about the multiplication, which is the crucial operation over fp to the m. When computing your pairing, it's the slowest operation, or actually maybe not the slowest, but actually the more, the most important operation. And here in this talk, I will present a very simple low area design, which is a parallel serial multiplier. So it's an iterative algorithm of completely quadratic complexity, so there is no optimization here. And just the idea is to take d coefficient of the second operand and multiply the first operand by those d coefficients at each clock cycle. So a way to represent this is this figure here. So you have your first operand A here, you have the second operand B there, and what you do is take, so for instance for this d coefficients equal to 3, you take the most significant, the 3 most significant coefficients of B, and then you take the 3 partial products, shift them according to the weight, reduce them modulo your irreducible polynomial f, and then compute the partial sum by just adding the partial products. And then you take the next 3 coefficients, and you go again, you shift everything, reduce mod f, and add. Okay, so since you process d coefficient per clock cycle, it means that you will require m over d clock cycles to compute the whole product. And this d is actually a parameter that you can fix, that you can change, because the area of your multiplier will actually depend linearly on this number d. So there is a trade-off here between either having a very small circuit but which will require many clock cycles to compute the product, or a larger circuit which will be faster. So the architecture of your multiplier will be basically this one. So you have the first operand here, which goes through all the partial products, and here you have the second operand in a small register where only the 3 most significant coefficients are distributed to the partial products. So then you have the shift here to shift the partial products according to their weight, reduction modulo f, and then a tree of adders to store the result, the partial sum. And then this partial sum goes through a feedback loop to be accumulated to the next partial products. So these multiplications here are only coefficient-wise multiplications over the small field fp. So if we are over f2, these are only AND gates, so very simple logic gates. The shifts here are actually just wires, so they come in for free in hardware. This reduction modulo f only requires a few additions over fp, as long as for f you've taken an irreducible polynomial of low weight. And finally, here for the additions, you only have, once again, coefficient-wise addition over your base field. So once again, over f2, these are only XOR gates. Now that we have all of these operations, we can make an actual coprocessor for the arithmetic over fp to the m. So here, very schematic design. So we'll have a register file to store the data, and here a bus for all the computational units to communicate with the register file. So we have our parallel serial multiplier, which, as I said, processes d coefficients per cycle, so computes a whole product in m over d cycles. And here we can have another operator which does at the same time addition, subtractions, but also can compute Frobenius maps. We can even complement our unified operator by adding a double Frobenius operation and a feedback loop, because if we look at the algorithm, we realize that there's a lot of iterated Frobenius to compute. So adding those two operations doesn't cost much, but actually makes a lot of sense. And, well, this is the actual architecture of the coprocessor, so I won't go into details, don't worry. But basically that's it. You have here your register file, here your adder, Frobenius, and so on, and here you have the multiplier from before. Okay, so now we have a coprocessor, we have an algorithm that we can map to this coprocessor. So the question is, how do we evaluate performance of this coprocessor? So here we counted all the operations from the algorithm, and what we can do, since we know how many clock cycles each iteration will take, we can schedule the whole computation of the eta pairing and compute how many clock cycles it will take. So here I have the number of clock cycles for computing the eta pairing over either my binary curve or my ternary curve. But yeah, well, okay, clock cycles, but then there's no use for them. I mean, what do they mean exactly? So actually, we will have to actually implement this coprocessor in hardware. So what I will do here is present an FPGA implementation of the coprocessor. So an FPGA is FPGA is an acronym which stands for Field Programmable Gate Array, and it's a reconfigurable integrated circuit, meaning that I can. So it's an integrated circuit on silicon, and I can reprogram it to have it execute any kind of circuit I want. And the idea behind it is that it's based on a matrix of logic cells. So there are all these small squares here. So all those logic cells you can reconfigure to have them do any kind of logic operation. And all those logic cells are interconnected through a routing matrix. So you can connect the output of any logic cell to the input of any other one. So basically with this, you can implement any kind of circuit, and it will be not that close, but kind of close of what you would get if you were to implement your circuit on an actual ASIC. So, well, okay, I can implement this on the FPGA, but next, what should I measure? How should I measure the performance of my circuit? So what are the metrics that I should look at? So the first metric, of course, is the area. That is the number of logic cells that my circuit will use. So it's actually the resources that I need to mobilize to execute my circuit, to implement my circuit. And then, obviously, there is also the time, or the latency of the computation. So how much time it will take to go through the whole computation. And a third metric, which is sometimes less known, is the area time product. So the product, actually, of those two metrics here. In fact, it makes a lot of sense, because maybe you'd have a circuit which is twice as fast as another one, but if it's not, if it's more than twice as large, then there's no point. You can just take two instances of the first one, and you'll be also twice as fast in less area. So computing this product, as soon as you're interested in throughput-oriented performance, makes actually a lot of sense. So the target FPGA I will be looking at in this talk is the Xilinx Vertex 4 family of FPGAs. So it's actually a mid-range family, so they are not the latest technology. They are already a few years old. And actually, it's a whole family, so it ranges from very small FPGAs, I mean very small, only 6,000 logic cells. And this FPGA will cost you somewhere around $150. And in this family, so as I said, you have several sizes, and the largest one is the 200 with almost 19,000 logic cells for a cost of $8,000. So there is really a whole range here between those FPGAs. But as I said in the beginning of the talk, I want to focus here on very low resource implementations. So actually, I will try to fit all my circuits on the smallest one here, so the LX15. Okay, so now I have my circuit, microprocessor, I have the ECC program that can run on it, I have my FPGA on which to implement the coprocessor, so now I can really measure the performance of this coprocessor. So here I've plotted on the x-axis the security, and here the time it takes to compute the ECC pairing. So I've done several experiments for various field sizes, which will range through this whole range of security levels. And I want to see exactly how much time it takes to compute each pairing at each security level. So, well, we have this kind of thing, which is actually no surprise. If you increase the security, obviously you will have to increase the computation time. So here I've written all the field sizes that were considered in this experiment. And the same goes for ternary curves. So it appears that ternary curves are a bit faster than binary curves, but that's not very important. What's important is really to see the increase here when you increase the security. Now let's look at the area that those coprocessors require. So same thing, on the x-axis the security, and on the y-axis the area. And you see that the area also grows, well, makes sense with the security. And actually very quickly, even before 90 bits of security, we are above the threshold. So we are above the size of the LX15, which was my target FPGA. So we are already too large. And if we want to reach the 128 bits of security, this is even larger than the LX40. So we have to take a really large FPGA there. And if I do the same in characteristic 3, then I have exactly the same kind of curve. And you see that very quickly, my circuit is much larger than my FPGA. Okay, so now what we can do, what can we do about this? So I really want to have a small circuit, but I also want to reach this 128 bits of security. So the first idea to tackle this problem was proposed by my student Nicolas Thibal at Pairing in 2010, and it is to use composite extension fields. So basically, if you take your pairing definition, so you remember that we have this tower of extension between FQ and FQ to the K, and all the operations in FQ to the K are actually mapped to operations over FQ. And, and here, of course, the critical operation over FQ will be the multiplication. It's, once again, the most used and one of the most expensive operations. And the arithmetic in FQ is actually covered by microprocessor. So here I can draw this virtual line because everything which is below FQ is done in hardware, whereas everything which is above FQ, so actually the arithmetic over FQ to the K, is done in software. All the operations here are mapped down to operations over FQ, which are then executed by microprocessor. And the problem is, this arithmetic over FQ, as you have just seen, does not scale very well to the 128-bit security level. The circuits are rapidly become huge. So the idea that Nicolas Thibal had was to actually introduce a subfield in between here FP and FQ. So this subfield would be here written FP to the M, and the field on which you would compute your pairing would be an extension, a degree n extension of fp to the m, so written here, fp to the mn. And then the idea would be that the hardware would only take care about the arithmetic over fp to the m, and all the rest would be done in software. Meaning that even though the hardware would have only a quadratic multiplier, everything starting from there and there as well could use subquadratic multiplication algorithms. Well, of course, if you do this, so if you define a curve over a composite extension field, then all of you may know that you introduce many weaknesses to the curve. And so you have to be very, very careful about the actual weaknesses that you introduce. So actually, this is the idea behind Nicola's work. It was really to study carefully those weaknesses and study the hardness of these attacks to make sure that it will not hurt the security, the overall security of the curve. So these attacks are mostly based on veil descent. So if you consider your curve here, so over a composite extension field fp to the m times n, you have that this curve is actually isomorphic to another variety which is defined over fp to the m, which is a variety of dimension n. So you get this by veil descent, and it was the basis for the Rodríguez-Smart attack, as this variety here might be actually the Jacobian of a curve of genus as at least n. And so, as you may know, curves of genus larger than 2 are subjected to index calculus attacks. And so the complexity of this attack would then be that one. And as you can see, it's still exponential, but it's not exponential in fp to the mn. So it's not exponential in the size of the field on which we compute our pairing, but it's exponential in the size of the small intermediate subfield. So that's something we really have to care about. And the other attack that can be applied to those curves is the static Diffie-Hellman attack, which basically happens when you reuse private exponents several times. And here, Granger presented an attack on this static Diffie-Hellman problem, which has this complexity, which is also exponential, but not in the size of fp to the mn, but only in the size of fp to the m. So it's only exponential in the size of the subfield. But then again, this attack, we can decide not to really care much about it, since a simple countermeasure would involve revoking keys after a certain amount of time. So what we can do is, if we fix the 128-bit security level, is to look at all the curves. So here I've taken the binary curves and see how we can split the field of definition of the curve so as to have curves which are secure enough. So here I've presented here p to the m. So the small subfield here will be the first, the first step, the extension degree n, so that we make sure that we have large enough subgroups in the curve. So here is the size of the subgroup, and here on those 4 columns I will print the complexity of the attacks. So all the curves obviously are subjected to Pollard's rho and FFS for the roots of unity at the end of the pairing. But as I said, there are 2 other kinds of attacks, namely the Rodríguez-Smart and the static Diffie-Hellman attacks. And as you can see, the complexity of these attacks diminishes when you increase this first extension degree n here. So obviously these attacks do not apply when n is 1, but as soon as you take composite extension fields, you are subjected to these attacks. But you might see that actually these attacks, they do not, so for instance, the GHS attack, they still have some high complexity. So we are not really threatened by these attacks. So here I've put in bold all the weak points of each curve, not really considering the static Diffie-Hellman attack. And so out of all these curves, for instance, we might want to choose this one, so which is defined over f2 to the 163 times 7. And as you can see, all the complexity of all the attacks is above 128 bits. So if we take these curves, then we are safe. And same goes in characteristic 3, where you have this complexity for the attacks. Okay, so now what do we have? So we have here the tower field here to compute every operation in FQ2DK as an operation over FQ. And we also have this part here, which is actually our hardware coprocessor. So the hardware part is already done. It's the same as previously. And the only thing that's missing is here, this extension here. So once again, we can just do this towering using polynomial representation. The addition, Frobenius, that is squaring or cubing, or is it compute, and it just remains that the multiplication will be the bottleneck once again of our computation, of our pairing computation. And well, since we've gone all that far to be able to do this in software, it will be kind of stupid to use quadratic algorithms here for the multiplication. So we will use actually subquadratic multiplications. So instead of 47 products here, you will require only 22, and instead of 15 products here, 25 products here, you will require only 12. Okay, so now I have my pairing. I can compute all the operations that I need over the extension field. Here in characteristic 2, here in characteristic 3. And then actually, since every operation can be mapped to an operation into the smaller subfield, I can compute exactly how many operations I need. And then implement this on my coprocessor as before. But then my coprocessor, even though it's a 128-bit security curve, will only perform arithmetic over f2 to the 133. So it will be actually much smaller than what we had before. So here, the percentage represents the percentage of the usage of this very small FPGA that I wanted to target. So as long as I'm below 100%, it means that I fit on my FPGA. So here you have the clock cycle count, and here you have the time which it takes to actually compute the pairing. Just for comparison purposes, here I present the other basic pairing, so over prime extension fields. And you see that these pairings were actually much larger, the circuits were much larger, but of course they were also faster. Since you mobilize more resources, your pairing will be faster. But then I have this pairing which is on a very small circuit, and this one is very fast, so how can I compare exactly the performance of those two? Well, that's where the area time product comes into play. So I can just multiply those two quantities here and see that the area time product for both of those curves is actually much better than the one for these ones. Meaning that even though I'm slightly slower, I'm actually so much smaller than it's better. Yeah. And just to present also results from the literature. Well, there are not many results about supersingular elliptic curves on the literature at the 128-bit security level, and the only one that exists is by Ghosh and others, which was presented at CHES 2011. But this one really did not care about having a very low resource circuit. Actually, the circuit that they presented is huge. It's almost 6 times the size of our FPGA. But on the other hand, it's very fast. But if you look at the area time product, you see that they are actually very similar. So we are not that bad. Even though we want to be very small, we do not sacrifice that much of performance. Okay, so another solution in order to decrease the size of our circuit while remaining at the 128-bit security level is to use hyperelliptic curves. So, well, genus 2 hyperelliptic curves are defined by equations of this type. And the only difference, I mean, not the only one, but a big difference with elliptic curves is that there's no group structure on the curve itself. So we have to go directly to the Jacobian, where we will actually manipulate divisors. So a generic divisor in genus 2 will have this form. So it will be 2 points, P1 plus P2 minus 2 times the point at infinity. We might also have degenerate divisors, which are only composed of 1 point, so effective degree only 1. And well, you have your basic addition algorithms. Instead of a line here, you'll have a cubic passing through all the 4 points, P1, P2, Q1, Q2. But then it's roughly the same. It intersects the curve in 2 other points, and then you take the symmetrics through the x-axis in order to obtain the resulting divisor dr, which is the sum of dp here and dq there. And as for the tape pairing, it's also exactly the same. So you take a hyperelliptic curve of a finite field fq, you take a large prime dividing the order of the group, then you have the L torsion as before, the L roots of unity as before. The MB degree is defined also in the same way, so it's the smallest integer k such that L divides q to the k minus 1. So the roots are obviously in fq to the k, and you can also show that as long as your embedding degree is larger than 1, you'll have, when you go to the kth extension of fq, you'll find other subgroups of the L torsion. And so your reduced tape pairing will have exactly the same form, where here you'll also have a Miller function, but this time defined over a hyperelliptic curve and not an elliptic curve. So if you're given a divisor, a d in the Jacobian, then the function, the Miller function here, will just represent the reduction of the divisor n times d into the reduced divisor n times d. And so we have exactly the same kind of inductive identity for computing the Miller functions, which then involves actually the reduction of the addition of n times d and n prime times d. So basically, if you have here nd and n prime times d, your Miller function will just be the ratio between this cubic and the 2 vertical lines. And once again, computing your Miller function that just boils down to a double NAT algorithm. The only difference here is that the iterations are more complex since they involve, well, here cubics instead of lines. So the curve that we consider in this work is so it's a genus 2 curve, obviously, defined over a binary field, so over f2 to the m by this equation. And this curve is also supersingular. So it means that there is a distortion map. So we have actually a symmetric pairing. Yeah, so the distortion map is like this. The group order is this one, as this form. So since we are over a genus 2 curve, the size of the Jacobian is actually the square of, I mean, roughly the square of the order of the base field. So here you have 2 to the m elements, and the order, I mean, the order of the Jacobian is roughly 2 to the 2m. And the embedding degree of this curve is 12. So this is why your distortion map ends up on the extension f2 to the 12m. So if we do as before, if we want to target 128 bits of security, then we will have to go to a field of size 2 to the 337. So this curve has actually a very interesting property, which you can put in evidence when looking at the octoplane of the curve. So first, let me take a point P on the curve, so xp, yp, and I will write dp, the corresponding degenerate divisor, which is just p minus the point at infinity. So this dp is on the Jacobian of the curve. So if I use Mumford representation, my divisor will be like this, and it will just be, as I said, p minus p infinity. If I double this divisor, I'll have, well, this equation. You really don't have to read it, that's not important. And I'll have here 2p minus 2.8 infinity. If I multiply again by 2, I have this equation. Once again, it's very boring, so you don't have to read it. But the point is, here, is that I still have 2 points. I still have effective degree equals to 2. So p4 plus p prime 4, p4 prime minus 2.8 infinity. But then, if I multiply again by 2, so I end up with computing 8 times my divisor, dp, you can see that here the Mumford representation, here the polynomial is only of degree 1, meaning that the effective degree of this reduced divisor is not 2, but it's 1. So actually I can write it like this, and I can have the multiplication by 8, so the octupling, acting not only on the Jacobian, but also on the curve, by this equation, which is actually very simple. And since the octupling acts on the curve, then we can also look at the form of the octupling Miller formulae, Miller function. And as you can see here, it has kind of a simple expression. So, well, by simple, really you have to trust me, it is simple, even though it doesn't look like it. So now with this, we can try and see how to implement a pairing on the curve. So the basic pairing that we have, so the Tate pairing with the double innet algorithm for computing the Miller's loop, will require 2m iterations, because L is roughly of the size of the Jacobian, which is basically 2 to the 2m. So this Tate pairing will require something of the order of 2m doublings. But then, if you remember the previous slide, we can also use the octupling formula which I've just presented. And so this way we'll have actually simpler iterations, and we can divide the size of the loop by 3 using only those simple Miller functions for octupling. So in 2007, in their paper about eta-T pairing, Barreto, Galbraith, and others have presented an eta-T pairing for this curve, where they replace the Miller function FLD1 by FTD1, where T has this shape. So basically T is of the order of 2 to the 3m over 2. So basically if you compute this Miller function using octuplings, you will only have m over 2 iterations here. So you can see that we've gone from 2m iterations to 2m over 3 and then to m over 2. But actually, we can perhaps go further. So when we started this work, we wanted to look at the optimal 8 pairing on this curve. So basically, the optimal 8 would be exploiting the action of the Frobenius on the curve in order to decrease again the size, this parameter t here. And according to Vercautren's work, one could go as far as to have something of the order 3m, m over 2 only for t, meaning m over 6 iterations when you do that only with octupling formula. But unfortunately here the distortion map psi does not allow for a simple optimal 8 pairing. You would need a much more complex distortion map in order to have the optimal 8 pairing working on this curve. So this would entail iterations which would be twice as expensive as the other iterations here, so that would not make much of a point. So actually we do not consider it here. What we've looked at instead was the optimal eta pairing. So instead of considering the action of the Frobenius, look at the action of the Verschiebung, which is the dual of the Frobenius acting on the curve. The problem was here that the 2th power Verschiebung, 2 to the mth power Verschiebung does not act on the curve, so you cannot use it to compute an eta pairing. But instead you can use the 2 to the 3 mth power Verschiebung, which this one acts on the curve. And with this, using this Jackson of this 2 to the 3 amps power Verschiebung, you can still increase a bit, decrease a bit the size of your the number of your iterations. So from m over 2, you can go to m over 3 here. So if we were able to use the 2 to the 3 amps Verschiebung, we would have m over 6. But here, unfortunately, we only have m over 3. So but that's still a 30% improvement when compared to the ATT pairing. Okay. Well, since I'm running late, I will quickly go through this. Basically, the idea is that some cryptographic protocols allow you to choose the form that you use for your divisors, so for the inputs of your pairing. And instead of using 2 general divisors, what you might consider is to have one of the inputs in the form of a degenerate divisor. So it means that it requires only 2 coordinates over the base field instead of 4 if you have a general divisor. And since the octupling acts on the curve, well, if you multiply by 8 degenerate divisor, then you end up again with a degenerate divisor. So since your Miller's loop is done only using octupling formulae, then you will keep having degenerate divisor. So you won't lose this property of the divisor being degenerate. And so we may want to compute either the pairing of two general divisors, but if the protocol allows it, then if we can compute the pairing of one general and one degenerate divisors, so that's what I write here, JD, we will basically have half as many iterations, half as many computations, half as many operations to compute this pairing as soon as one of the divisors is degenerate. And fortunately, lots of protocol allows this. And we might as well think about pairing 2 degenerate divisors. So this will halve again the cost of the computation, but there are far less protocols compatible with this optimization here. Okay, so now I have this pairing, which I can implement on my coprocessor once again. And so this coprocessor will be designed for F2 to the 367, and I'll have this count of operations. So you see it looks a bit the same as usual, but you have many multiplications, additions, and so on. And as I said, so this was for the general times general divisor. And as soon as I include a degenerate divisor, then my operation count drops. So basically it drops by a factor of 2 each time I have a degenerate divisor. So that can represent a huge improvement in terms of performance. And just to finish, here is the benchmark of the coprocessor realizing this pairing. So the area will still fit on the smallest FPGA that I wanted to use. And the computation time will be somewhere around 3.5 milliseconds. And if I compare with the other implementations, you can see that this is perfectly on par with the other ones. The area time product is a bit larger, but once again, I'm using the generate times generate pairing, general times general, and as soon as I will have a degenerate divisor as an input, I can divide my cost here by 2, or even 4 if I have 2 degenerate divisors. Okay, so just to conclude, well, here we've reviewed several implementations of supersingular curves, but there's something that we cannot avoid, is that supersingular curves are really handicapped by their very small embedding degree, which is bounded, so we cannot do better than 4, 6, or 12 for the curves that I've presented. And since this embedding degree is very low, it's really hard to keep up with today's security requirements without losing too much in terms of performance. And actually, this presentation was only for 128 bits of security, so I'm not even talking about 192 or 256 bits. The problem is, well, if these curves are not that great, why do we have to implement them? Can't we just do without them? Well, unfortunately not, because supersingular curves are the only one which allow for type 1 pairings, so symmetric pairings, which are still required by some protocols. And, well, they have another advantage, which is really, they are the only pairing-friendly curves over small characteristic fields. So, and small characteristic arithmetic is really suited to low-resource systems when compared to large prime field arithmetic. So, yeah, really keeping the resource usage to a minimum while trying to keep up with the security levels is really becoming a challenge at the moment. And there are still many open questions that we might want to pursue. So just to see how this composite extension field technique will scale if we target larger levels of security, and also how the optimal 8, which we decided not to look into at the moment, will behave over this hyperelliptic curve I was talking about. And there are also further research going on. So, for instance, looking at computing pairings with theta functions, which could also improve the number of operations that are required to compute the pairing. But in any case, whatever we may do, it really gets harder and harder to compete with ordinary curves such as barytoneric curves. So, for instance, just to give you a teaser about the following talk, this optimal 8 pairing on a barytoneric curve requires only 338 microseconds to compute, and with actually a very small amount of resources. So please stay tuned for the next talk, and thank you very much.
Thank you very much for the nice talk. We have time for 1 or 2 questions. Quick questions. Yes, please.
Yes, I was just wondering how you discovered that octupling acted on the curve. Was it by experiment, or is there some theoretical results?
So actually, this was already exploited by Barreto, Galbraith, and others in their eta-T pairing paper. So this was already there. So that's also why we chose this curve. It was because it has this nice property. We didn't discover it by ourselves.
One more question? Yes.
So from the implementation point of view, so I see you have a lot of squarings, for example, multiplying by 8. Yep. Did you also consider using normal basis? Because that would be much faster to square itself.
Yeah, but then your multiplication would be more expensive. And I mean, in hardware, squaring is really, really fast. In software, of course, you'd rather have normal basis because shifting is so much more easier. Is much more easier than actually computing the linear combination required for the squaring. But in hardware, computing a linear combination of only a few elements is extremely easy. So there's no much of a point looking at normal basis at this point.
Okay. Yes. One more question, please.
Have you looked at instead of double and add to using other addition and subtraction chains, which might actually save you some?
Yeah, sure. Well, actually, for supersingular curves, their group order is has such a nice shape. I mean, when you look at it in base P, actually the algorithm is not a proper double and add or triple and add algorithm. It's just really looking at the base P decomposition of the exponent to which you, I mean, of the scalar to which you multiply your point, and so it's a custom, I would say, addition chain or addition subtraction chain, where you'll have where you choose all the formulas, all the functions to really match your scalar.
Yes, please. Yes.
So we have used subquadratic multipliers, but only for polynomial basis, not optimal basis. But then it was for, so the objective was not the same. We really wanted to compute pairings as fast as possible. So this is why we resorted to subquadratic multipliers. But then again, it was fully parallel subquadratic multipliers, so the area of the coprocessor was huge. So that's why I haven't really talked about it in this talk, since here in the talk the objective was to keep the resource usage to a minimum, which we were not able to do with subquadratic multipliers.
Okay. One quick question I cannot resist. Inverse Frobenius operators you are not using, Jérémie?
Yes, we are, of course. Well, since you're familiar with this work. It's just that I didn't want to present this in this talk. Okay. But yeah, of course, for some irreducible polynomials defining your field of p to the m, it might turn out that computing a cube root or a square root is as easy as computing a cubing or a square, or even sometimes easier. And you can rewrite the whole pairing algorithm based on inverse Frobenius maps. So square root or cube root instead of squarings and cubings. And so this will not impact the number of operations that you will have, since they will require basically exactly the same number of operations. It's just that the performance of your circuit will be slightly better because you'll have faster square root than squaring, or faster cube root than cubing.
Okay, thank you. Let's thank the speaker again.